Alright, partial derivatives 14.3. This is going to be a really short video. We're going to talk about two things. We're going to talk about how to take partial derivatives, which you really should know if you're watching this video already. If you're skipping class, amazing. I understand. And what else? The other thing I'm talking about then is implicit differentiation and what that really means. So, okay, let's take a look then at this problem 14.3.44, which is find all the second order partial derivatives. Okay, and well, what are the second order partial derivatives? Well, they comprise of d squared. You have the, let's say you have a function, right? F of x, y, z is equal to something, and your second order derivatives are going to be d squared f partial of x squared. All right, so two partial with respect to x, d squared f dy squared, which is two partials with respect to y, d squared f dx dy, which is going to be a partial with respect to y, and then a partial with respect, well, a partial with respect to x, and then a partial with respect to y, and d squared f dy dx, which is going to be a partial with respect to y, and then a partial with respect to x. So these are all the second order partials. Okay, and so in this problem then we're given f of xyz, or they call it something else. Oh, okay, so it's not even xyz, it's h, or okay, so if there is a z, then we have to include the z guys in here as well, but let's just say f of xy, and so these are the four partials that go with f of xy, okay, and h, then in this problem we have h of xy is equal to x e to the y plus 1. All right, so we need to find all the partial derivatives. And what are they? Well, okay, so first of all, in order to find the second partials, we have to find the first partials. So the partial of f with respect to x, well, what is that? Well, we hold the y's, we treat the y's as if they were constants, right? So then this first guy then, or this is not df, but this is rather dh, because the name of the guy is h. Doesn't really matter. And okay, so take the partial with respect to x. What is that? Well, we look at this first guy, and we treat the y term as if it were constant, right? And just take the derivative of x, which is 1. So then this becomes e to the y, right? And over here, what happens? Well, okay, the derivative of x dy dx, right? The derivative of y with respect to x, since y is a constant, you can like think in your mind that y is like 7 or something like that, right? Just replace y with a constant in your mind, and that's 0. So then that's e to the y plus 0, and then of course the constant with respect to 1 is also 0. So dh dx is equal to just e to the y. All right? Cool. Now what is dh dy? Dh dy is going to be equal to, so you have x e to the y, right? But now you treat x as if it were a constant, so you have some constant multiplying e to the y, and then take the derivative of e to the y, which is still e to the y, so you still have x e to the y, all right? And then now you take the derivative of y with respect to y, well, that's 1, and then derivative of 1 with respect to y is 0, and so that's x e to the y plus 1. All right, so now we can take our second partials. What is then dh dx squared, dh squared, d squared h dx squared? Well, that's then just the partial of x with respect to this first guy. So I have e to the y, right? And what's the partial of x with respect to e to the y? Well, there are no x terms in e to the y, so the partial then of e to the y with respect to x is going to be 0. Right? And then I got d squared h dy squared. So I look at this guy right here, and I look, okay, what's the partial of this guy with respect to y? Well, this first guy then still remains x e to the y, right? Because x is a constant, and then the derivative of e to the y with respect to y is x e to the y, and then, or is e to the y, and then x multiplies that. And then the derivative of 1 with respect to y is 0. Right, so that's x e to the y. So the second partial with respect to x is equal to d squared h dx squared, and the second partial with respect to y is d squared h dy squared, and that's x e to the y. All right, Cool. Now what do you have? We have mixed partials. So now we got d squared x, d squared h dx dy. So I got to take this first guy and take the derivative with respect to y. Well, that's easy because I got e to the y, take the derivative with respect to y, and that's e to the y. And then d squared h dy dx. So I got to take this second partial up here, dh dy, and then I got to take the partial of this guy with respect to x. And what is that? Well, now, right, e to the y becomes a constant, and I take the derivative with respect to x of x, right? So e to the y is the constant, the derivative of x with respect to x is 1, okay? And then, so I get 1 times e to the y, so that's equal to e to the y, and the derivative of 1 with respect to x, well, that's a constant, so that's 0, so it's e to the y. And so we have our 4 partials, 4 second order partials. I want you to notice that these two mixed partials, no matter which order we went, are equal to each other, right? E to the y is equal to e to the y. And that's not a coincidence. That's going to happen every single time. So when you have to find mixed partials, you only need to go in one. You only need to go one way. It doesn't matter if you want to do dx dy or dy dx. You'll get the exact same thing. So that is good to know. It makes sense. And so that's going to be how we find second order partials. You have to find the first order partials, and then you have to, differentiate from there. Okay. Cool. Let's continue on then. And now we're going to take a look at implicit differentiation. Which talks, okay, so what is implicit differentiation? Well, it's essentially you treat as if one variable is like a function of another variable. So, for example, the example that I always use, it's in my notes, and it's from the book, is 14.365. So you want to find the value. Actually, let's go through a different example. Let's not use that book one. That book one's in my notes. Let's pull one up on the internet. Cool. So let's see. I want to find the partial of z with respect to x, where you have x cubed minus x cubed z squared. Oops. X cubed z squared minus 5x minus 5xy to the fifth z is equal to x squared plus y cubed. Okay. And that's a 3. So what does this mean? So essentially, we're treating z as a function of x. So essentially, we have this function z of x is equal to something. I know that's really weird to think about, but we don't know what z of x is, but we're treating z as if we're a function of x, and we can find the partial dz dx. So what does this mean? How do we do this? Well, keeping this in mind that z is a function of x, so that means we can take its derivative, right, with respect to x. Now, let's take a look. So we got x cubed z squared minus 5xy to the fifth z equals x squared plus y squared. Oh, and that's a x squared plus y cubed. And that's a glitch. All right, so, okay, what do I want to do? First step is to move everything over to one side if you can. So that, and then minus x squared minus y cubed is equal to 0. Okay, so I want it equal to 0. Cool. All right, now what? Now I want to go through and just take the derivative with respect to partial derivative with respect to x. So I'm going to go through and I'm going to take a partial derivative with respect to x of this entire thing on both sides, really. But what's the partial derivative of x with respect to 0? Well, that's still 0. Okay, so I'm going to go through and take the partial derivative with respect to x. Now, keep in mind, z is a function of x. So keep that in mind. Give this a shot if you want. You can pause here and give it a shot. Remember, z is a function of x, so you have to use some special rule when you take this derivative, partial derivative. Okay, I don't blame any of you guys if no one tried to do this. But what happens then is, okay, so I take the partial with respect to x. That's cool. So what happens? I get 3x squared, right? So that's the partial with respect to x, z squared. So that's keeping z constant while taking the partial of x. But remember, z is a function of x. So I have to apply the product rule, okay? And now this is essentially 3x squared z squared, but I took the derivative with respect to x, so there's a dx dx, right? Okay, does that make sense? Because I held z constant, I took the partial with respect to this x cubed term, so now I get 3x squared dx dx. We just never write this because dx dx is equal to 1, right? Dx over dx is literally equal to 1. And then now I have to add, well, I have to add x cubed to z, right? Because now z is a function of x, right? Z is a function of x, so I got to use the product rule. And now I have, because I'm holding z squared, right? I'm taking the derivative with respect to z squared. I got dz dx, right? Does that kind of make sense, right? We have used the product rule. Over here, I'm taking it with respect to I'm holding z constant and taking the partial with respect to the x term. Over here, I'm holding the x constant. I'm taking derivative with respect to z, which is a function of x. And so I have then dz dx, and over here I had dx dx because I took the partial with respect to x, okay? All right, so again, this derivative, that one guy is responsible for all these terms because of the product rule. All right, what's next? Well, now I have to conquer this 5x to the 5x y to the fifth z term. So again, I take the everything else except the x constant and take the derivative with respect to x, and I get 5y to the fifth z dx dx. All right, and then I get minus 5xy to the fifth, and then the derivative of z is 1, but then I also have the remaining dz dx, okay? And some of you guys are going to be like, wait, what about the y? Well, y is a constant with respect to both z and x, right? Because I'm not looking for dy dx or dz dy, right? So y is just a constant. We just treat y as a constant when we take the partial with respect to x here, all right? Next term, I got minus x squared. Well, the partial of that with respect to x is going to be 2x, and then really 2x dx dx. And then minus y cubed, well, what's the partial with respect to y cubed of x? Well, again, y is a constant with respect to x, so that's going to be minus 0 is equal to 0. Okay, so now let's clean this up a little bit. So again, dx dx, that's just 1. Dx dx is 1, dx dx is 1. So I got 3x squared z squared, all right, plus x cubed 2z dx dx, or dz dx, whoops, it's a crucial mistake there, can't mess that up, all right, minus 5y fifth z, minus 5xy to the fifth dz dx, and then minus 2x is equal to 0. We want to find dz dx, so how do we do that? Well, we move everything that doesn't have dz dx over to one side. So now I got x cubed 2z dz dx minus 5xy to the fifth dz dx is equal to, all right, this becomes positive 2x, right? So 2x, and then here's a positive 5y to the fifth z, and then this becomes a negative 3x squared z squared. And then the last step, factor out this dz dx, right? And now you have x cubed 2z minus 5xy to the fifth is equal to the guy on the right-hand side still. It's the exact same. And then dz dx is equal to 2x plus 5y to the fifth z minus 3x squared z squared divided by x squared 2z, or x cubed 2z, but let's call this 2x cubed z. Let's just pull the constant out in front. It's better looking. Minus 5xy to the fifth. Okay, so that's the partial derivative of dz dx. So hopefully that makes sense, right? When you're taking dz dx, z is a function of x. So the top guy is going to be a function of the bottom guy, so you got to be careful when you take the derivative of dz with respect to x, okay? And so that was a product rule. This guy was all of this guy. That's also the product rule. It's the same rule, and that's how you implicitly differentiate. So we're going to be revisiting implicit differentiation again. I might revisit this exact same example in the next section, which is the chain rule. And yeah, let's just move on to that section then, which is section 14.4.